Hi everyone, it's Mr. H here. This video is about solving any triangle, whether it's similar triangles, right triangles, or non-right triangles. In the description, you'll see a link to the handout that I'm going to use for this video. Feel free to use that and follow along. So the first question I'm going to look at with you is how can you show if triangles are similar? What properties are helpful? Now notice on the triangle ABC, we know 3 side lengths as we do on triangle DEF. And so what we're going to do is we're going to do side, side, side similarity. We're going to look at the ratios of corresponding sides between those two triangles. So starting with side DE, we're going to compare that to side AC. And so those are both diagonal lengths on those two triangles, so it makes sense those would be the corresponding sides. So 26 divided by 13 gives me a ratio of 2. I'm going to do the same thing with side AB compared to side EF. So EF over AB, the bigger side over the smaller side, just so that we get a number bigger than 1 as our ratio. And so that's 10 over 5, that gives us 2. And I'm going to do the same thing yet again with sides DF and BC. And so DF is 24, BC is 12, and that again has a ratio of 2. And so because all those ratios are the same, that means those two triangles are similar. But we have to be careful with how we label this, because the vertices need to be in the same order. So we did ABC. A corresponds with vertex E on the big triangle. B corresponds with vertex F on the big triangle, so that's the next letter. And then vertex C corresponds with vertex D. So we say triangle ABC is similar to triangle EFD by side, side, side. Now look at the next situation. We now have an angle and 2 sides. And so we have side, angle, side similarity that we're going to try to show in this next situation, which is different than side, 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 as you can see. And so what we're going to look at is we're going to look for, first off, the ratios of sides are the same. So we're going to start with DF, compare that to AB, 10 over 5, that's 2. And we need this other ratio to be the same as well. So EF, that's the other side we know on the big triangle, divided by AC is the big side, the longest side on the small triangle. That again gives us a ratio of 2. So this seems to be that these are going to be similar triangles, but we don't know unless we also check one of the angles, and we know that one of the angles is the same. And it's clear that they're both 90 degrees. Therefore, triangle ABC is similar to triangle. If you want, pause the video and see if you can label what it is, but it's F that corresponds with A, and then D corresponds with B, and then we end with E. And so that's triangle ABC is similar to triangle FDE by side, angle, side. Now the third situation is just angle, angle. If we know 2 angles in one triangle, we know they're the same in another triangle, then we know those 2 triangles are similar. This is the easiest one to check. And we can see just from the diagram that they both have 67-degree triangles and both have 90-degree angles. So triangle ABC is similar to triangle D, that corresponds with A, so the order matters. E corresponds with B, and then F. So this one is nicely in alphabetical order, while the other ones were not, and that's because of angle, angle. So those are the 3 ways. Now we're going to apply those to this situation. So it says find the length of DE in the drawing below. So it's worth noting first off that the 2 angles I've just shown there are going to be opposite and the same. And then we have these parallel lines as well. And so those parallel lines form some interesting patterns, one being the Z pattern. And so that forms, that means that ABC is the same angle as DEC. And then if we draw a Z the other way as well, it means that angle BAC is the same as angle CDE. And so all we have to do is show that 2 angles are the same. And so we're going to start by proving that similarity, which I did just talk you through, but let's see how we would write that down. If you were writing a test, this is what you would be expected to do. So you'd say angle BCA is equal to angle ECD. And that's by opposite angles. And so those are the first angles I labeled there. And then you could pick one of the other 2. And so angle ABC is equal to angle CED. You could have labeled that DEC. Doesn't matter, just provided the E is in the middle between those. And so those are called alternate angles. That's the Z pattern. And so we know that those 2 triangles are similar, which is now going to allow us to calculate things with those similar triangles. So we can say, therefore, triangle ABC is similar to triangle D, corresponds with A, angle E correspond with B, and C corresponded with C. So triangle DEC by angle, angle. So now that we've proven that they're similar, we're going to solve the length of DE. And so in order to solve the length of DE, we're going to set up a ratio between values that we know versus the one value we don't know. We don't know what DE is, so I'm going to write that on the top because it's easier to find what I don't know when it's in the numerator. And I'm going to write that over the corresponding side on the small triangle. And so that's AB. And then on the large triangle, I know CE, and that corresponds with the length of BC on the small triangle. And so now I can put all those values in. The only thing I don't know is DE. So I have the length of DE over 8.2, and that's equal to 24.0 over 9.3. And so now it's just a matter of rearranging that to solve for DE. And it's really as simple as just multiplying by 8.2. 8.2 on the top and bottom, the left cancels out. And then we multiply the 24 by 8.2, divide by 9.3. The 24 times 8.2, if you wanted to do that intermediate step, you don't have to do that necessarily. But if you did, it would give you 196.8, and your denominator being 9.3 would give a DE value, a length of DE of 21.2 meters. Then you want to do just a quick mental check to say that's a little bit shorter than 24, just like 8.2 is a little shorter than 9.3 on the small triangle. So now what we're going to do is we're going to move on to 90-degree triangles. These next two examples have to do with 90-degree triangles. Now, normally with 90-degree triangles, we have the Pythagorean theorem. And so the Pythagorean theorem is something that you've been working at for years with, and that's a squared plus b squared equals c squared, where that c value is the hypotenuse. Now, that's all well and good if you're trying to find a third side if you know two of the sides, but what if we know angles that we're trying to solve instead? If we're trying to solve angles instead, we now use SOH CAH TOA. And so the SO stands for sine is opposite over hypotenuse. The cosine stands for adjacent over hypotenuse. And the TOA stands for tan equals opposite over adjacent. Now it's worth noting that sine, cos, and tan all operate on an angle. They're not multiplied by an angle. They need that angle to operate on. So let's just go over what those opposite, adjacent, and hypotenuse are. If the angle is drawn like so, the adjacent is the angle beside it that's not the hypotenuse, and the opposite is the opposite side of the triangle. Now, I've labeled the angle here up at the top. The opposite side is the side opposite, and the adjacent is right beside. So it's important to keep that in mind. The opposite can change, and can the adjacent, depending on where the angle is that you're referring to. So with that in mind, let's look at this first example. Determine the value of x in the diagram below. Now you can see that the opposite side is x and the hypotenuse is 20.2. And so that would mean we need to use the sine law. So sine says opposite over hypotenuse. We sub in the angle of 42. The opposite side is x and the hypotenuse is 20.2. And then we just multiply both sides by 20.2 in order to get x by itself. It cancels off on the right side. And we get x equals 20.2 times sine of 42 degrees. Make sure your calculator is in degrees, and you'll get the answer of 13.5 meters. Sometimes your calculator could be in gradians or radians, and so it's very important that you make sure it's in degrees when you calculate these. So there you go, 13.5, it's shorter than the hypotenuse, that makes sense. On the triangle below that, you can see that the opposite side to the angle is 14 and the adjacent is 11. So that requires us using the tan ratio. And so tan is opposite over adjacent. And so we go tan of the angle, we don't know the angle, is 14 over 11. In order to get the angle by itself, what we have to do is we have to do an inverse tangent. And so in order to do that, we go tan inverse by putting that little -1. And what this is done in your calculator usually is if you do shift and the tan button. It's usually just a color above the tan button in your calculator. And so we do tan inverse of 14 over 11. We can't just divide by tan because it's operating on the theta. So this undoes the theta operation. And when we put that in our calculator, we get 51.8 degrees. And that should make sense because if the angle is bigger than 45, the opposite should be longer than the adjacent side. Now we're going to look at the sine and cosine law and when you can use each of these situations. So this only applies if you do not have a 90-degree triangle. If you have a 90-degree triangle, by all means, go back and use SOH CAH TOA. Don't waste your time using these. If you don't have a 90-degree triangle, here's the sine law. Sine A over A equals sine B over B equals sine C over C. You'd use that version of the sine law if you were trying to solve an angle, because it's in the numerator. But if you were trying to solve a side length, you'd actually use the reciprocal of that. A over sine A equals B over sine B equals C over sine C. And the thing to remember is you're only ever going to use a pair of these at a time. So A and B, B and C, or A and C. It all depends what you're trying to solve in a given triangle. And so what we want to note here is that the bottom version is the version that you are going to use if you're trying to solve a side length, if you don't know a side length. And the top version, on the other hand, is the version you're going to use if you don't know an angle. So it's just, like we said, it's just a reciprocal of the other. So it's nothing big that's changed. It's just you flipping everything in the fractions. Now we move on to the cosine law. The cosine law says this. It says that c squared is equal to a squared plus b squared, which is very similar to the Pythagorean theorem, but there's more to it now because it's not a 90-degree triangle. So it's minus 2ab cosine of angle C. Now we can rearrange that equation if we were trying to solve for the angle C. It would become c squared. We subtract a squared and b squared from both sides. So we get c squared minus a squared minus b squared. And then we divide by the negative 2ab in front of the cos C. That would cancel out. And then we just take cos inverse of everything that's left on the left side. And so you get cos inverse of c squared minus a squared minus b squared over negative 2ab. There's a video I'm going to mention at the end that goes into more detail about how to do that if I went over that too quickly for you. It's also in the description below. So in the first version, it's when we don't know one of the side lengths. In the last version, it's when we don't know an angle. And so we're going to look at when we use each of these beyond that now with a couple of just situations that we're going to see below. So on the left, we're going to look at the first situation that we're going to use the sine law for. And that is a situation where we have pairs of known things, at least one pair, an angle and the corresponding side that we know. So if we know side angle, for example, so a situation might be like 10, 14, and 36. We have two sides that are joined to each other, and then an angle that is not in between those two sides. The other way you can think about it is that that one side pairs up with the angle that's across from it. And then what that would allow us to do is it would allow us to solve the angle that's across from the side that's 14. The other situation would be angle side. And so that would be a situation where we know two angles and the side opposite one of those angles again. And so you can see there, we've got 36, then 40, and then it's not the side that's between those two angles, it's another side that we're using. And so that allows us to solve the side that's opposite the 40-degree angle. So side angle, angle side, those are the two situations when you can use the sine law to solve. What about the cosine law? The cosine law can be used when a triangle has side, angle, side. I like to say a triangle is giving you SAS. When it's doing that, we cosine it. And so that was a situation where the angle is actually between two known sides. And so I want you to notice here, there's no pair of side with the opposite angle, or no angle with the opposite side that pairs up and we have those two values for. We never have a pair like we did in the sine law. So the cosine law is used in that. In the first case of the cosine law, that's what we'd use in the side angle side. And the other situation you run into with the cosine law is if you're given all three sides. And in that case, you'd use the rearranged form of the cosine law for the angle. And that's what we're going to do a little bit in some examples to follow. So this example says solve for angle A in the triangle below. And so in this case, we have a pair of side with an angle, or in other words, you could look at this as being side angle. And so we know we're going to use the sine law. And so the sine law, if we're trying to solve for an angle A, means that we want to write sine A on the top. So we start with sine A over A equals sine of capital C over C. And so what we're going to do now is sub in everything we know. We know that little a is 14, the length of A, and we know that the angle C is 36 and little length C is 10. So we want sine A by itself, so we multiply both sides by 14. Now I'm multiplying the right side by 14 in the front just so we don't complicate it and think that the sine is operating on the 14 as well. It's not. So don't ever make the sine operate on the 14. Don't go 36 times 14 or anything like that. So the 14 divided by 14 cancels out, and we're left with sine A is equal to 14 times sine 36 degrees over 10. So remember, because the sine operates on angle A, in order to get sine to the other side, we have to do sine inverse. And so that's going to be shift sine on our calculator. And so the way you would type that in most of the time on your calculator is you type in the 14 times sine 36 degrees, divide it by 10, get that answer. It's 0.822899 repeated. Goes on from there. And then you can take sine inverse of that by getting shift sine, and you get an angle of about 55.4 degrees. The last example we're going to look at is solving for length b of a triangle below. And so this triangle is giving a side with the angle and then another side, so side angle side. That means we're going to use the cosine law. The other thing you can do is you can look at pairs of angles with known sides that are opposite. There's no pairs. So we know we have to use the cosine law. Now notice here, because it's side b we don't know, we're writing the cosine law with b squared equals a squared plus c squared, the two sides we do know, minus ac times cosine of b. That little length, that little b, the length of b, has to correspond with the angle at the very end. And all the other letters are for the other two sides. So what we get is b squared equals 14 squared plus 10 squared minus 2 times 14 times 10 times cosine, and we sub in that angle b, 104 degrees. Now in order to get the length b by itself, we have to take the square root. So we take the square root of all this. 14 squared is 196. 10 squared is 100. And then 2 times 14 times 10 gives us negative 280. And then the cosine of 104. And here's where a lot of people make a mistake. They take the 280 and the cosine of 104, and they don't multiply that first. You have to remember your orders of operation. You must multiply that before subtracting it from the other numbers. So if you've done that properly, what you end up getting is 363.73813, and it goes on from there. After taking the square root of that, you get 19.1 meters. And you'll notice that because that's opposite the 104 degree angle, that should make sense that it is the longest side on the triangle. So always ask yourself that when you finish the question. Does that make sense according to the diagram that I have labeled earlier on? For more on the sine and cosine law, check out the video on the right. For more on SOH CAH TOA, the trigonometric ratios for 90-degree triangles, check out the video on the left. Thanks so much for watching. Please like and subscribe if you found this helpful, and comment below what you found to be the most challenging part of this video. Thanks.